Hi there, this is your instructor Ryan Chatterson, and during this session we're going to be covering RAS, Engineering and Design Fundamentals. So RAS by definition stands for Recirculating Aquaculture System. This is an aquaculture production system that recirculates water by utilizing life support technology to maintain the aquatic organism's standards of health. Some of the standards for recirculating aquaculture systems are open systems, which are flow-through, meaning the water's coming in to the tank, exiting the tank, and it's the same water's not returning to the tank. So that's not actually a recirculating aquaculture system, but that's a flow-through system. Then we get into partial reuse systems, where maybe we're using 50% of the water, reusing that, and the rest is getting discharged. Then we get into recirculating aquaculture, which is 70, 80, 90% recirculating, and the other 10% coming in as fresh water. 80% reuse and higher is common for recirculating aquaculture systems. Zero discharge, however, is uncommon and difficult due to the extra processes involved, specifically denitrification, and the expenses that are incurred by doing those processes. Aquaponics and other forms of integrated agriculture help to solve this issue. Indoor versus outdoor recirculating aquaculture systems. So, indoor controlled environments allow for maximum control over temperature, lighting cycles, and biosecurity. So biosecurity meaning animals, theft, birds, anything that can come in and harm your facility. It's favored for its predictable year-round production. And here's a picture of an indoor recirculating aquaculture system. This was actually Bell Aquaculture. You can see it's all lit up. Beautiful array there, all in an indoor controlled environment. Here's another picture of an indoor controlled environment RAS system. Now, outdoor RAS. So this is favored because of the lower upfront capital investment. So it's cheaper if you don't have to build a building and control the environment around those tanks. This is favored in regions with acceptable climates for the species that they are growing. So in the Virgin Islands, growing tilapia, an indoor facility like this might not be something that's needed. Whereas if you were in Bermuda, it would definitely be needed because it's a lot colder going up north to that island. Dependent on local restrictions based on the cultured species and its proximity to water. So if you're growing a species that is, say, non-native to where your location is, and you have close proximity to natural bodies of water, you may not even be allowed to culture that species. It also has to depend on your waste output and how close you are to, say, watersheds or other important sources of water that could possibly be harmed by the waste production from your aquaculture facility. It's very location specific. RAS pros. Some of the pros of recirculating aquaculture are that there's a much smaller area requirement. Because we're doing intensive culture of these species, we don't need anywhere near the land area that we would need in, say, pond-based aquaculture or something of that nature, because we have much higher stocking densities with life support that can handle that. We have reduced water usage. So we have a normal flow-through system that may be getting 1,000 gallons per minute flowing into these tanks. And if it's flowing through, it's going 1,000 gallons per minute out. So they have a high water usage there compared to if we had a 90% recycle system that was only using 100 gallons per minute input into the system. So if we can drop the water usage by 90%, it's extremely resource efficient compared to the other means. We have increased biosecurity, and especially when we have this housed in an indoor facility. So we won't have birds diving down and harming stock. You have a very high decrease in the risk for anybody coming in and stealing any equipment off of the premises or stealing the product themselves, poaching the fish off your farm. So there, and again, you also have a decreased risk for any kind of diseases or pathogens entering into that water that's going to harm your stock. And that is huge when we're looking at maybe a smolt facility growing 5 million smolt a year. You need a closed facility, and you don't want to have to use any kind of pharmaceuticals, any kind of antibiotics to treat infection in the fish. And by having a closed indoor facility with a closed water source, then you can avoid using all antibiotics in fish culture. We have better feed conversion rates because the fish are under tighter control and tighter watch in a recirculating environment. We can feed them more, and we can get them to grow faster and utilize that food better. So that's really big. It costs us less food to produce the same animal in the end. Controlled environment is definitely preferred for predictable year-round growth. So fish growth will change when temperature changes. In an outdoor environment, it's going to be really hard and expensive to control the temperature in a tank. Think of a screened-in back porch and trying to air condition that porch. It's going to go right through the screen into the environment. It's very hard to control temperature in an outdoor scenario. But in an indoor environment, we can control the temperature in the entire building and the temperature in the culture water. And that allows for predictable year-round growth. And that's what you need to sell crops of fish. You need to know when you're going to harvest that fish so that you can line up buyers that are ready for when the harvest day comes. And it's much easier to monitor the health of the fish crop when you have them swimming around in a tank in a building right in front of you than it is if you're having to net them out of a pond and find the crop, do it when they're feeding. It's much harder to monitor everyday fish health outdoors than it is indoors in a controlled recirculating system. Some of the cons. The top con here is it's a high initial investment. It's not cheap to buy all of the tanks and all of the equipment to raise fish on land. So that's the biggest con. There's a high risk involved with raising high densities of fish in a controlled environment. So you have very little time to respond to any kind of catastrophe that might happen. There's limited experts in the field of aquaculture. Now there's several out there, but when we look at the big picture, there is limited expertise. And unless you have the money to hire a consultant or you have the knowledge and experience behind you, it can be very difficult to deal with some of the problems that arise, especially in an intense type of grow out. And the regulations can be difficult depending on your location and your size. So some locations will be very smooth. They already have fish farmers operating, and the laws will already be so that it is acceptable for fish farming in that area. In other locations, you may be the first one that's trying to start a recirculating aquaculture system, and you're going to have a harder time going through some of the regulations in order to get set up properly and begin production. So those are some of the cons that you may experience. Now we will get into some of the common recirculating aquaculture equipment that you're going to see in everyday operation. Culture tanks. So that's the fish tank, but we will refer to that as a culture tank throughout the rest of this course. Mechanical filtration. Now, mechanical filtration is the filtration that pulls out the solid material from the water. So your solid fish feces, say a dead fish that floats through, scales that are dropped off, any solid matter is what the mechanical filtration is going to pull out of the water column for us. Biological filtration is what we talked about earlier, our nitrifying bacteria. And biological filtration is going to process our dissolved nutrients, like ammonia, into harmless nitrate nitrogen. Chemical filtration would be used to disinfect and treat the water. So this would be UV sterilization, this would be ozone usage, and maybe even hydrogen peroxide, which we will talk a little bit about all this later. Water pumps, which we need to move the water from the low point to the high point and to recirculate water through the fish culture system fast enough to get the waste nutrients out of that water and maintain water quality. We have aeration and oxygenation equipment. So if we're using ambient air with air pumps and air delivering equipment, we refer to it as aeration. If we're using an oxygen generator, pure oxygen gas, something of that nature, we're going to refer to it as oxygenation equipment. We have degassing equipment. So gases are created through fish actually eating food and the entire biological filtration process, and we're going to need to remove those gases from the water column, CO2 being the main gas, and for that we need degassing equipment. Water quality monitoring equipment. So this would be to monitor your dissolved oxygen, to monitor the pH in the water, to monitor maybe the conductivity. We have water quality instrumentation that allows us to monitor that equipment on spot checks or in some cases on a continuous basis. And then we have one of the most important things, emergency alarms and backup equipment. We need emergency alarms in case we have low dissolved oxygen, or in case we have a power outage, in case a pipe breaks and water goes on the floor. It's nice to have emergency backups so that when and if these happen, it doesn't become a catastrophe. You can actually get in there and fix the problem when it happens. Okay, culture tanks. So preferably round in size for their self-cleaning capabilities. So being round in size allows the internal water hydraulics to bring the solids to the bottom and then to the center drain quickly and efficiently to remove them from the water column as quickly as possible. That leads to keeping better water quality for the fish that are actually swimming around in there. Square with rounded corners will also work because we can still get a circular velocity if we build a tank that way. A multi-cell raceway is another way to do things, which we'll talk about here in just a moment. The biggest thing here is that the correct dimensions are very important for optimum water quality, water velocity, and everyday workability. Again, if you need to get into the tank and it's 10 feet deep, might be a problem. Here's a picture of some beautiful tanks made out of cement. You can see nice dimensions here. Here are some octagonal tanks made out of a wood frame and a liner. So a little bit less expensive of a way to go and pretty space efficient when you look at the way they have this set up in the facility. 3-to-1 width to height ratio is optimum for a round tank. That's optimum to get the water hydraulics to do what we want them to do. So you have to be careful over a 4.5-to-1 width to height ratio, or you'll get an irrotational zone near the center of the tank. and basically it will stop drawing solids to the center. They will fall short and they won't make it right into the center bottom drain. We want to size the tank based on the maximum stocking density of fish at the time of harvest. So what is the most fish that are going to be in there at any possible time? That's what we size the size of the tank off of. The aeration, for aeration-based designs, should not exceed a ½ pound per gallon or 60 kilograms per cubic meter. For beginners, you should shoot for half of that. Shoot and design for a ¼ pound per gallon or 30 kilograms per cubic meter. Designs utilizing oxygenation should not exceed 1 pound or 120 kilograms per cubic meter unless the user is experienced. And there are certain species that can go up much higher than that. Tilapia can go up above that, and trout can go up above that. Something like an African catfish can go up substantially higher than 1 pound per gallon. So a center bottom drain outlet for smaller tanks or tanks with in-tank aeration. So when we have aeration being employed in the tank, we don't get the same water flow characteristics as if we dissolve oxygen into the water flow before it gets into the tank. Use a drain plate or a guard above the center bottom drain to keep waste trapped once it gets close to the center and to keep fish away from the tank outlet. So I'll show you later how we're actually going to build these cheaply and efficiently, and it will really help the waste export from your tank by installing the proper drain. Proper tank design with center bottom drain makes the tank self-cleaning. This is the biggest factor. I've been a lot of places and had people tell me that they have to get in and scrub the bottom of their tank or scrub their tanks once a week to make sure all of the fish waste makes its way into the drains. I haven't ever scrubbed the tank to move fish waste since we've been in operation, and that's because we have the correct velocities within that tank. So here's a picture to give you an idea of what we're talking about here. And we have our flow outlet right here. This is where water flow is coming into the tank. And again, I'll show you how to construct these a little later on. And the water flow is coming in here. We actually have two outlets in this picture, and it's coming in here as well. And we're going to inject it in a circular velocity. And as you see here, the waste is going to drop down to the bottom, and it slowly makes its way into the center of the tank right here. And that is the self-cleaning mechanism that we're looking to create. On top of this flow, there's a secondary flow that's going to be happening in this manner and in this manner at the same time that we have our circular velocity happening. So as this secondary velocity happens, it's drawing waste down to the bottom and into the center of the tank before it rises back up into the water column. So that as well helps to draw solids into the center bottom drain. Now if we employ aeration into this tank, say down the sidewalls, that creates an uplift current wherever we have an air stone, and that interrupts the circular velocity that we've created within the tank. It interrupts the tangential flows and it interrupts the radial flows that help draw that waste to the center. So again, at the bottom, tangential flow will give the tank a profile that naturally draws settled solids towards the center. Oxygenation will not disrupt this flow, but in-tank aeration can. And here's a picture of our water outlet. As you can see, it goes all the way to the bottom of the tank. It's capped off, and then we have the correct number and size of holes drilled in that distribution outlet so that we create the right velocities within the tank. And here is a manometer, and we will talk about that a little bit later as well. And that's basically a means to look at the flow rate that is created by creating differential back pressure through a reduction fitting. And we'll talk about how to build that a little bit later as well. And here is a nice picture of some tanks that I installed. And with the correct water outlet and the correct velocity of water, you can see it creates a very nice circular effect that's strong enough to create a whirlpool 4 feet up from the center bottom drain. Now, I haven't actually put a drain plate over this yet, but once we do, it will kill the vortex and you won't see that at the top of the tank. But that's just to show you the force that's created by employing the right engineering skills and engineering the flows correctly, which you will all be doing after we finish this course. So now we're moving on to Cornell dual drain tank design. And this is a dual drain design for larger tanks or smaller tanks that utilize oxygenation. There's 2 outlets. So we have a center bottom drain like we just talked about, but then we also have a sidewall skimmer box. So think about this like a swimming pool. The big square box on the side of a swimming pool, we do the same thing on the tank. The side box is going to pull 80 to 90% of the water out of that. And that's considered relatively clean water because our solids are dropping to the bottom of the tank and concentrating in the center, right at that center bottom drain, because of the hydraulics within the tank. So 80 to 90% through that sidewall box, and 10 to 20% of the dirty water is going to leave through the center bottom drain. Now, why do we do this? What is the advantage of employing this type of system? Well, it allows, for one, for a smaller radial flow separator, that's what RFS stands for, or swirl separator to treat the dirty water stream before both of those streams meet and go through secondary solids filter, such as a drum screen filter, an upflow filter, or a settling tank. So, in the end, it means we can use smaller filtration to pull out the solids. Filtration is based on the flow rate going through that device. And if we can drop the flow rate by 80 to 90%, then it can be that much smaller, which means less money in that device. It can be less of a footprint. So advantages all around. It concentrates that waste in a smaller area. Here you can see a beautiful picture of crystal clear water, and they're employing a dual drain outlet. So you can see there's a center bottom drain located right here, and there's a sidewall skimmer box located here. So you've got 80 to 90% of the flow leaving through here, and you've got 10 to 20% leaving through here. This will go directly to a first stage solids filter, like we'll talk about in a little bit, but it'd be a radial flow settler or a swirl separator. And then from there, it would meet up with this waste stream, and they would both go to the next device, which pulls out, it's a secondary filter, but it pulls out the fine solids and the suspended solids that are left in the water column. So there's multiple center drain outlets. We're moving on now, and we're talking about a multi-cell raceway. And in a multi-cell raceway, there's multiple center drain outlets that go down a long rectangular tank. So the rectangular tank is divided up into square compartments, and water inlets are placed in the corners of these squares to create a circular flow around a center bottom drain. So if you think about a 5-foot by 20-foot rectangular tank, if we divide that up into 4 5-foot by 5-foot compartments, then we have 4 squares. Each one of those squares, we would put the water outlet into each of the 4 corners of the square. Each outlet would point towards the next outlet, and that would create a circular velocity within that square. And then we would put a center bottom drain in that square, creating, theoretically, a circular tank within that square within the larger rectangle. and we can separate those cells by screen so that the water quality is the same within each of the cells, but the fish cannot swim from one to the next. This is very space efficient because, again, a square tank versus a round tank, you get the corner area, so you can always get more water in a specific area using a square tank. And this eliminates plug flow that is common in raceways. Plug flow means if you have a long raceway and then you inject water into the front end, your waste is going to accumulate as the water goes down the raceway. And you're going to get one single flow, not equal flow throughout that entire raceway. So it will basically find the path of least resistance, and you don't get equal flow throughout that entire water volume. So what happens? Your fish will crowd up by the inlet in the upper third to quarter of the raceway, and very few will swim in the water further downstream because it's of lower water quality. And here is a picture of a multi-cell raceway, and you can see it's a long rectangular tank. It's divided by screens, individual compartments, and the water outlets creating the flow are actually underwater. Moving on to stocking density. One of the first questions we need to answer is the stocking density of fish, or what's the fish to water ratio? After we know the stocking density, we can size the culture tank, calculate the feed, and design the system components for the rest of the build-out. So now we're going to get into a little bit of math. And for all my non-math people out there, don't worry. So I'm going through these formulas for everybody that wants the hard math so that they can get the exact calculations for themselves, which is really needed during large-scale commercial designs. But after each one of these, I'm going to actually give you rules of thumb or a quick guide so that you can skip this step and choose a safe number without going to the extreme. And again, any questions, email me and I will answer them during the question and answer session.